Welcome to Lecture 13. Today I'm going to be talking about non-premix combustion and then getting into misfire. So in the last lecture we focused on premix combustion, in which case we had a flame that was triggered by a spark, and that flame had a laminar and a turbulent flame speed, so it was a deflagration. We briefly touched on detonation, but we weren't focused on that as a type of combustion. What we were mainly concerned with was the homogeneous reaction. So this is what leads to knock. This is putting fuel and air in a box, and at a certain pressure and temperature, they automatically ignite in what is essentially an explosion. And the goal of our engine design is to have the deflagration, the laminar flame speed, filled and go all the way from the spark plug to the far wall before the homogeneous reaction can occur. Today we're going to move on to the non-premixed combustion. So on the premix side, the flame was a function of how quickly the chemical reaction could occur. In non-premixed engines, the limiting factor is how quickly the fuel and air mix. So we're talking about droplets evaporating, if we're spraying fuel in, how quickly the turbulence can mix that fuel with the air, and that's going to occur slower than the laminar or turbulent flame speed, and even slower than this homogeneous reaction. Typically we're going to design our non-premix engines at a higher pressure ratio, so it's going to be at a higher pressure and temperature so that this homogeneous reaction is really fast, and as soon as the fuel and air mix, we can basically assume it's combusted. So what we need is very fast mixing, and that's what we build into the diesel engines. Some examples of non-premix flames. So these are the Hollywood special effects flames. A candle, you have basically the fuel is in the wick, the air is surrounding it, and you get some natural convection that replenishes the air while the fuel stays centered. And it's only at the point where fuel and air meet where there's this cone flame. Other examples would be our diesel engines, a flamethrower, a campfire, burning coal. All of these are non-premix flames because the fuel and the air are not perfectly mixed prior to ignition. So in the last lecture we had this reaction zone that moved forward or backwards in one direction. So it moved in the direction of a mixture of fuel and air, and behind the reaction was products. In this case, you can imagine we have this surface perimeter here where air is on the outside and fuel is on the inside, and right where they meet is where the reaction occurs. And so if this is a jet of fuel coming from the left hand side of this image, the center of that jet won't burn until it's been able to mix out to the edge where air is. So if you were to plot the fuel concentration, on one side there's some high concentration of fuel, and as you get close to where the reaction is occurring, the reaction is consuming that fuel, so there's going to be virtually no fuel in the area of the reaction. Same idea with oxygen from the other side, and in the area of reaction we have a high concentration of products, because as soon as the fuel and air meet, they react. Then we need some external force that is mixing this oxygen and this fuel so that this reaction zone moves to another place, or somehow moves more of this fuel to this location where it'll meet up with more oxygen. So this video wasn't working last time I tried, so I'm going to go straight to YouTube and show it there. And you can see the spray of diesel coming into the engine. This is just before top center. And you can see in this next segment a whole lot of ignition points. So each of these little bitty flames is an ignition point, and it burns all of the droplets of diesel fuel all throughout the engine. And then you had some wicking along the walls, and that fuel formed a sheet of fuel along the edge, and then that burns. Let me close that down. So in those areas near the walls at the end, you get something similar to premix fuel, but throughout the entire engine, you had those individual droplets that were burning. This next animation shows it in a little more detail. Because it's an animation, they can zoom in. But the things I want you to note is how they spray the fuel in different segments, and then take particular note of the shape of the piston head. And that shape is there to create swirl and help with the turbulence as it combusts.
Fuel lines connect the injectors to the rail. A stable pressure level is maintained at all times for the injectors of all cylinders. The quantity and length of the injection can be controlled electronically at any time, regardless of the crankshaft angle. Bosch solenoid valve injectors control the nozzle needle so quickly that the injection process can be divided into pre, main, and post injections, up to 8 separate partial injections per power stroke. The pre-injection serves chiefly to reduce combustion noise, and the post-injection to reduce internal engine particulate or to raise the exhaust temperature. The high pressure results in a very finely atomized spray of fuel. Tiny fuel drops exhibit a large surface area in relation to volume. That promotes a speedy combustion process on the one hand, and on the other hand, helps reduce the particulate mass in the emissions.
So this visualization helps you see the droplets and how the edges of the droplets are evaporating, and it's right at that point that the flame occurs. So that evaporated fuel mixing with the air creates these streaking combustion events. The other thing this video illustrated was something we can do with direct injection specifically for diesel engines. Because these gases in the cylinder are at such high pressure and temperature, as soon as the fuel gets in there and as soon as it mixes, it's going to react. We don't need a spark plug. So what they're able to do is spray a little bit in first so that there's not this very sudden increase in pressure in the cylinder. So the forces on the piston can be smoothed out. So that's why they do the first couple sprays. Then the main spray event is happening as the piston starts to travel downward. And then they mentioned a final cleanup spray, which is trying to scavenge some other droplets and ensure everything gets combusted. So we also now hear all the time about gasoline direct injection. And I want to point out some of the critical differences between the diesel direct injection, which we've always had to do for diesel engines, and the gasoline direct injection. What you're going to notice is this injection occurs during the intake stroke, long before the combustion occurs. And the shape of the piston head is very different. The goal of these piston heads is to try and facilitate some higher concentration of the fuel in the area immediately around the spark plug. and it will create this tumble motion that I'll point out when the video ends.
The fuel is directly injected into the cylinder. Thanks to the optimized wide bowl on the piston and the injection during the compression stroke, an optimal mixture of the fuel and air is formed near the spark plug, and this leads to a clean ignition.
So if you notice, there were some little gray droplets that seem to have this motion. That's what we'll refer to as tumble. So squish was when the cup that has this sort of a shape created these swirl eddies. Tumble is a bulk motion from the gasoline direct injectors, creating a single large tumble motion. So another video of an actual engine, this being a gasoline combustion, and you're going to see a spark plug from this right side here, and the flame will very quickly propagate from right to left. So basically, before the piston has moved much at all, the flame is able to reach this far side. Flame's already there, piston had barely moved. So we can put these two types of combustions together in theory, and we get something called high compression charged ignition. You can also think of this as controlled knock in a gasoline engine. Now to date, no one's actually commercialized and sold engines like this. It's very hard to control the spontaneous ignition to happen at exactly the same moment in every cycle. We can get pretty close and fairly stable for steady highway driving, but that's very different than when you put the pedal to the metal or let off the throttle. So Mazda is actually bringing to market in 2019 what they refer to as their SkyActiv technology that will still have a spark plug for certain modes of operations like high power, but for steady highway driving, something like 80% of the typical engine use, it will operate in this high compression charged ignition mode. This video, it tries to show it. It's a slurring image, so you get the shadow graph basically, and you can just barely see the combustion event where throughout the entire region here it all burns simultaneously. It puts a lot of stress on the engine, but it makes for a efficient and complete combustion. The other advantages of HCCI is that we can burn leaner mixtures in a gasoline engine. With the spark plug, we need to have something closer to stoichiometric to ensure the flame can propagate fast enough. In these high compression charged ignition, we can operate leaner the same sort of way that we operate our diesel engines. The high compression ratio also improves the efficiency of the engine. The problem is just controlling that spontaneous ignition to basically be at a specific moment that we're controlling. It's difficult to do, and those slight variations in air and fuel between cycles causes the instabilities in these engines. So if we were to plot things out of where these different type of combustions occur in terms of equivalence ratio and flame temperature, your normal spark ignition combustion engine, it's running at an equivalence ratio of 1. It's the highest temperature combustion, and our primary concern is the formation of NOx. The diesel engine, even though we're running lean when you account for all of the air in the cylinder and all of the fuel in the cylinder. Locally, where it's actually burning at the edge of the droplets, it's actually burning rich. So we have less of a concern of NOx and more of a soot concern with our diesel engine. The quicker we can get those miniature droplets to evaporate, so the smaller we can make those droplets, we'll move up this curve and hopefully operate in this sweet spot between soot formation and NOx formation. And that's where diesel engines, clean diesel, is trying to operate. The high compression charged ignition is a pre-mixed engine, so we don't have any local rich versus lean areas. What it allows us to burn at lower temperature where we can be slightly lean, and then we're out of the NOx region, we're not forming soot, it's very efficient and quite clean. But making it stable and repeatable is difficult. So the last part of this lecture is I want to talk about misfire. So we've already introduced the problem of knock, which is if the flame front is taking too long, then the residual fuel and air mixture in the corners will spontaneously combust before the flame has gotten there. And the way to avoid knock would obviously be to speed up your engine at higher RPM, higher flame speed. We don't have enough time for the homogeneous ignition to occur. So engine knock typically occurs at low engine speed. At higher engine speed, our concern is more in terms of misfire. So those slight variations between cycles can change the equivalence ratio substantially. And in one cycle, there may not be enough fuel in the area immediately around the spark plug, and when it fires, it may not produce a flame that propagates through the cylinder, so it misses the fire. We can, in a laboratory, burn gasoline at an equivalence ratio of about 0.5. In an actual engine, we start to see misfire in spark ignition engines somewhere around an equivalence ratio of 0.65 to 0.75. And that depends partly on the RPM. So faster flames will avoid misfire just as they'll avoid knock. The main times we're worried about misfire is when the engine's running really fast and we've throttled the engine back. So you hear this in race car engines when they let off the throttle and you hear that banging out of the exhaust. Those are the misfires. What's occurring is we've throttled the engine so the air coming in is maybe 50, 60 kilopascals. So it's very low density air coming in, and what that means is we're going to leave more residual in the engine. Less is going to be pushed out by that incoming air, and that extra residual is products of combustion. It doesn't have fuel in it, and it dilutes the fresh air and fuel coming in. And that's the major thing that leads to misfires. So in one realm, we have to worry about knock. In the other direction, we have to worry about misfire. And don't worry about the details of this slide. What I want to get at is just sort of this evolving window of where we can operate in terms of equivalence ratio to avoid both knock and misfires. So when the engine's cold, we can basically run in a pretty wide region from stoichiometric to an equivalence ratio of about 0.7, 0.65. As the engine really heats up and the air coming into the engine is hotter and less dense, we'll move in this direction and we'll start to run into problems with knock. The higher, if the air is starting at higher temperature before we compress it, it's going to be even higher temperature when we finish compression, and that's going to speed up that homogeneous reaction, which leads to knock. So the higher the intake air, the more likely we are to knock, so we need to operate slightly leaner. Um, the sweet spot in terms of adiabatic flame temperature is somewhere between 2100 2200 degrees. We tend to avoid NOx formation, but we're right on the edge of misfires. So again, this is just reiterating that the flame speed is a small function of pressure, not as much as it is a function of adiabatic flame temperature. So when we drop the pressure on the intake, it slows down flame speed and leads to more misfires. For misfire, the biggest thing at a given engine speed, when we suddenly throttle back the engine, that is the most likely time to worry about misfire. Turbulence, more turbulence on a higher flame speed, is there turbulent flame speed, that limits both misfires and knock, but again, too much turbulence extinguishes the flame. So we need turbulence to a point, and that's our main design feature with how we shape the piston head, how we shape and control the spray of the fuel coming in. All of those things are creating the precise amount of turbulence that we want. Another way to avoid misfires is to add multiple spark plugs to your engine. A lot of race car engines often do this with multiple spark plugs. So I'm going to conclude today with a little example. This is basically just a geometry problem. The last two lectures have been heavy on the concept of knock and misfire and the different features of combustion. This is trying to highlight how in a spark ignition engine the flame doesn't move at a steady pace. For reasons of how the spark plug works, we want to have a rich air to fuel mixture in the area, maybe a very small volume immediately around the spark plug, just to get the reaction going. And you can think of it as having enough critical mass, critical energy release that the flame will propagate. So we need that right around the spark plug, but the rest of the engine, and on average, the engine can run quite lean. So once that flame is going, it can propagate through a fairly lean mixture, in this case 22:1. The flame speed of the rich flame and the lean flame are very different. So let's take in this example that in that rich region, just the 2.5 centimeters immediately around the spark plug, the flame's going to move pretty quick, 28 meters a second. In the slower region, the rest of the cylinder, it's going to move at 17 meters per second. So in this design, we'll imagine we have our cylinder, pistons here, the top of the cylinders there. We have some center line, and the spark plug is going to be offset 1.5 centimeters. And then the spark advance is going to be 12 degrees. So that spark is going to fire 12.5 degrees before the piston gets to top dead center. And for this area immediately around the spark plug, the flame will move at 28 meters per second. And then from that point to the far edge, it's going to move at 17 meters per second. And then finally we have this ignition delay. So from the moment the spark fires to when the flame actually starts taking hold and moving is 1.25 milliseconds. And the goal of this question is to find what is the crank angle when the combustion is ended, or when the flame has reached the far wall. So in this example, I think other things we'll need to know is the speed is 1800 RPM. We need that it's a 2-liter 4-cylinder with a crank offset of 4 centimeters to get to the bore and these lengths. So I'm going to switch over to OneNote and go through the details, or the solution to this problem. A moment while I get there. Okay, so the first thing we need, let's sketch out what's happening. We've got our cylinder, pistons in there. It's connected. Let me draw the top here. If there's a center line, our spark plug is 1.5 centimeters from the center line to the spark plug. And we need to know, oh, the other thing is this distance of 2.5 centimeters. It's going to be burning at 28 meters per second. And then for the remainder of this, it's going to be burning at 17 meters per second. So our goal here is really just to add up the time. There's 1.25 milliseconds for the flame to start. There's some amount of time, and we'll call that T2, for the flame to burn through the rich region, and then time T3 for the flame to burn all the way to the wall. And let's find out those 3 times, and then we'll convert that time to a crank angle. So to finish out the geometry, we need the bore of the engine. That's going to be the total volume displacement over 4 cylinders times, we need 4 over S times pi, and that's to get to bore. So we have a bore in this case of 0.089 0.0892 meters, or 8.9 centimeters. So a typical engine size. So the time T2, we know there's a hemisphere here that's 2.5 centimeters in radius, I believe, that will burn at 28 meters per second. So T2 is going to be that distance, 0.025 meters, 2.5 centimeters, divided by 28 meters per second, and that's going to be 8.93 times 10 to the negative 4 seconds. And then the third part of the flame is going to burn, how far is it going to burn? Well, from center line to here would be half the bore, and we've offset the spark 1.5 centimeters in this direction, and that first flame burned 2.5 centimeters. So we're at a point here 1 centimeter away from the center line and all the way to the edge. So that's going to be half the bore plus the offset minus the 2.5 centimeters. And we'll divide that by the 17 meters per second. And when I do that is 2.035 times 10 to the negative 3 seconds. So if I get the total time of combustion, so we'll call that T total, is going to be equal to the 1.25 milliseconds that it took for the spark to ignite the fuel, and then plus the time to burn in the rich region, which is 0.893 milliseconds, plus this time to burn all the way to the wall, so plus 2.035 milliseconds. And I don't actually have that written down because I did it in terms of crank angle. So if I get the data at the end of combustion, so C end is, whoops, where'd that go? Data C end is equal to the engine speed times 2 pi, or 360 degrees if we're doing it in degrees, times the time. So that is the crank angle of combustion minus the spark advance. So in this problem, we have an engine speed of 1800 revolutions per minute, and I'm going to do it in degrees. So there's 360 degrees per revolution, and then I need it in milliseconds, or seconds, either one works. So I'm going to need to do 1 minute over 60 seconds, and then multiply by whatever this t total was in either seconds or milliseconds. And then I'm going to subtract the 12 degrees of spark advance, and I will get 33.1 degrees. So that's taken some amount of time. We started the spark 12 degrees before top dead center. We've finished the combustion 33 degrees after top dead center. The piston has probably actually moved a significant amount during that combustion event. Well, that concludes this lecture.